All right. So Wx, y, z prime. Here. W prime xy, W prime x, y, z prime here. What habis? Okay. Wx prime, y prime, z prime. Here. X prime, y prime, z, z here. X prime, y prime, z prime here. Keluar pula landasan. Okay, and then here. Okay, so putting inside, and then we have to do the Carnot map, yeah? The Carnot map. So if you still remember, it's the power of 2. 2 to the 0 is 1, 2 squared is 4, then 8. So you circle the biggest one, do the biggest one first. The biggest one will be, right? And every single entry you have to circle and take the biggest one if possible. So this and this is like a cylinder. So you can do the two together. If you do circle like this, it's not the minimum, right? So you have to do the biggest circle. And this can combine like, because it's 2 to the 1, okay? And from here, this is, it cover W prime, gone. It cover Y, Z prime, right? Z prime, W prime. So it's just X prime and Y prime. Okay, you see what it covers. This one, these two, W prime, W plus W prime is 1, right? So just X prime. And for this one, it covers Z prime and just Y prime. Okay, and this, it covers W prime, okay, but only X, right, and YZ prime. This is how you get the term, right? This one, it covers W prime, so you just take the X, and this is this YZ. Then after this, this is the minimum expression, yeah? So F min is X prime, Y prime plus X, Y, Z prime. Many questions in the end of this chapter, you should try all, okay? And with this, you draw the logic gates, X, Y, Z. Then you have how many gates? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So when you draw, you will have 7 gates. I will not ask you to draw this because there will be so many gates. Okay, so okay. Dah lama tak dengarkan saya punya okay. Okay. Okay, Fatana, Emilia, Neha. Okay. Ada tak yang gini? Gini ada kan? Ada emoji tu kan? Okay. See, it's okay. Alright, so I will, mana pula pergi pemandang? Okay, so I will continue with, where did I stop last time?
Billion group.
Ya, tapi di mana? A billion group. Okay. So that's chapter 6, yeah. Yeah, algebraic structures and groups, yeah. Next sikit lah. Dah buat pun habis. Okay. Okay. Saya tak panggil nama lah. You just, kalau tak ada yang bercakap, somebody has to turn on the mic and help me. Okay. What are groups? What is the first property? Ulang balik semula. It has to be close, right? It has to be close, means the binary operation is defined for the set. So we can use like this, right? Ataupun sometimes we use just a dot. G for the set and the operation. Okay, close means A, B for all A, B in G. A dot B is also in G. Yeah, okay. The second one is associative, meaning A, B, C is A, B, C. Third one is identity. Yeah. Okay. And that exists. I normally use E, although sometimes they use I. In G, that exists. Actually, this E is unique, but sometimes people don't put. Tanda suruhan tu is unique, but as long as you put that exists, it's already okay because there is no other identity. You have to know how to prove that the identity is unique. Nanti kita masa kita cuba ya. There exists a unique E in G such that A times E is A, which is E times A for all A in G. If you don't remember to write in symbols, you can also write in words. There exists a unique identity in G, but you have to remember because sometimes the operation is different. They give you something weird, okay? So you have to use this property to find your identity like we did last time, right? Remember, I give you a different operation and find the identity. And you have to show that the identity is multiplied on the left and right. Not only left and right. And the last one is the inverse. Okay. For all A in G, there exists also, this is actually unique. You don't get different inverse. B, or we call it sometimes A inverse. And it has to be in G. Okay, not only that we have the inverse, it has to be in G such that okay, such that A times A inverse is equal to A inverse times A, meaning it has to be both multiplied right and left to be the identity. So in order to have the inverse, you have to have the identity first. If the set does not have an identity, don't worry about finding an inverse. You won't get the inverse. Okay, the identity first. Multiply on the left and right. And we have gone through some operations before, right? If you have integers, it has to be addition, right? So if it's okay, if this is integers, to be a group, you have to have this operation addition. Or maybe some other kind of addition operation that is not normal. Because if you use multiplication, under addition, for any group, for any numbers under addition, the identity is
0.
0. Type dekat chat pun boleh. Okay, sebab saya tengah pandang screen. Okay, for multiplication, the identity is
1.
1. Okay, so we do have identity for both addition and multiplication. But the inverse for this one, for all A plus what is 0. So the inverse is the negative. And negative of integer is also inside, right? And if you still remember, I mentioned that you have to think first before you write anything for this chapter, right? Think first before you write anything, because you look at the question. If the question gives you integer, positive and negative are inside. If I change the question, like I put positive here, so it starts with 1, 2, 3, 4, right? Although it is still okay, it's still close. Positive plus positive is positive. Associative, yes, this is true for numbers for under addition or multiplication. But identity under plus is always 0, it's the normal plus, but 0 is not in here. Yeah, so the identity, you don't say it exists because it's not in there. So you will put, what do you want to find? E, A plus E is A. So under addition, this will give you E is 0. Okay, E is 0, but 0 is not in Z plus. So once you write this, you will say that the inverse does not exist. Don't say that the inverse is 0, but it's not inside. You say that the inverse, the identity does not exist. Okay, so for this one, the identity does not exist. You stop and you say it's not a group. Okay, and I also mentioned last time, to show something is a group, you have to find one flaw only, one property that it does not satisfy. You don't have to show 1, 2, 3, 4. So in the next time, if you are given a question, you think first, you don't need to write everything because it won't give any mark. Because if you want to show something is not a group, then you have to show some property is not satisfied. You go through that property, just write that down, and your mark comes from that particular property only. But if you have to show something is a group, then you have to show every single one. Okay, so for example, for this one just now, right, this is a group. So you have to start from the beginning. If the question is show that integers under addition is a group, you have to show from the beginning. So you can say that the integers under addition is a group because, or is closed because an integer, the sum of two integers is an integer. Whatever you write in your reason, if it gives the right reason, it's okay. Don't worry about English, don't worry about your sentences. The sum of two integers is an integer, okay? Or an integer plus an integer is an integer. I will accept that. The sum of two positive integers is a positive integer, right? That one you don't have to prove because it's a fact, but you have to state. And then for associativity, you don't have to show because this is what we know from before. You just write down A plus B plus C is A plus B plus C. Okay, so enough on this one, right? There is a special name, right, for this? This is called a semigroup, right? And this is called a monoid. Then if you have all, this is called a group. And we stop at abelian group. So abelian group, we add another property in which G is commutative. G is commutative means AB is BA for all AB in G. All right. So additional property for a group, whether it's abelian or not. And you know in the back of your mind that if it's under addition, A plus B is B plus A, right? A times B is B times A. Matrices, A plus B matrices is B plus A. So you have to know your linear algebra also. But A times B for matrices is not necessarily B times A. So most matrices, they are not formed, they do not form abelian group. Ada bunyi sikit. Ada third floor, ada renovation sikit dekat bangunan ni. That's why that's the drilling. Okay. But you can still hear me clearly, right? Yeah, okay. Okay, so this is abelian group. If I give you this question, dah pernah bagi hari tu, tapi rational number ada under multiplication. Is this a group? So you think multiplication, yeah? And this is numbers, they're all rational numbers. So you have to think about what is actually this Q. So this is fractions, right? Fractions, A over B, in which A, B integers, and B is not 0. Okay, the best way is to look at some examples inside. Okay, you have integers also in here, you have 0 in here, you have negative, right? Then you think for this set, you multiply two fractions. Do you get a fractions? Okay, yes. Is this defined? Yes, because if this is in here, B is not 0. D is also not 0. So you know this is also not 0. Sometimes we take it for granted, but you have to show, if the question is show that this is a group or this is an abelian group, if, yeah, or decide, okay. One type of question, decide whether this is a group or not. Okay, as I said, probably you think no, it's not a group because the inverse does not exist, right? For 0, right? 0 times what is 1? Okay, so you just write that particular property is not a group because 0 has no inverse. Okay, there is no B. This is how you should write your answer, yeah? One of the ways to write. 0 has no inverse since there does not exist 0 inverse because we use the inverse like this, right? In Q, that satisfies this, right? 0 times 0 inverse, we want it to be 1. We want it to be the identity in Q. But you can look at So this is the reasoning on decision of this is not a group, right? So the question is decide whether this is a group. So the answer is no, since 0 has no inverse. Okay, this is, if this is the question, this would be the perfect answer. If the marks is 2 marks, 1 for here, 1 for here, 1 for here. But the question can ask you this: show that this is closed under multiplication. Okay, that is another question, right? Maybe not this question, but just to give you Q and multiplication, show that this is closed under multiplication, meaning you have to prove this. You have to prove, yes, it is closed because A over B times C over D is AC over BD in Q. Why is it in Q? Because it satisfies this, right? That is a story. It's not just, okay, you multiply 2 fraction, you get fraction. The story is, given A over B and C over D in Q, meaning A, B, C, D, they're all integers. This is not 0, this is not 0. When you multiply, this still integer, this is still integer, right? Because integer times integer is in integer. And since this is not 0, this is not 0, this is also not 0. So you have to write all those down because that is the main question. So read your question very carefully. I did not say at all that this chapter is hard. No, but you need to think first, think carefully, and then you write down. Okay, don't write away, yes, no, you have to think. Okay. Okay, and then you decide whether it's an inverse, right? Let me give you another example. Tomorrow I will start with the subgroup. Okay, we have a subgroup, we have normal subgroup, and we have a quotient group, and we also have homomorphism and isomorphism for this particular chapter. If you also taking or have taken modern algebra, this is all very familiar to you. In discrete, it's just 1 chapter. In modern algebra, it's 1 semester, right? And if you take masters, we have masters in mixed mode. There's also class called group theory 1, and then later group theory 2, which talk more about groups. Okay, so group can be learned for 1 to 2 years. If you further on, like Kak Hana here, then you see groups, or later on you call it rings, right? You can look at it again for at least 3 years. So you see, there is a lot of things, but in this class, we just do I call it a surface, right? Just for 1 chapter. Okay, let me give you another. Okay, before that, before I erase, any question? Is it okay so far? Okay, okay, okay. All right. Okay, let's try. I have 5 minutes, yeah? Let's try. Question from, what's my note just now? Okay. Oh, I also mentioned about Kelly table, right? Last time, the Kelly table is multiplication table in which every row and column has to have only 1 element, and the row and column that is the same as the top row or left column is the identity. And to find an inverse, you have to look at every row or column and find the corresponding, right? The corresponding element to be the inverse of each other. Okay. Okay, we have this example 620. We have a G G is the set of all non-zero real numbers. G in R, G is not zero. The set of all non-zero real numbers under this multiplication. Why we exclude zero? You know the reason, right? Because we don't want the inverse to not be in the set. If zero is in, we don't have an inverse. That's why we take out zero. Sometimes we write this like this. Okay, this is the real number without zero. This backslash means minus. Sometimes we say like this, right? Minus. Because we want it to be a group. Okay, first question is show G is an abelian group. It's very funny. Sometimes the question gives you to decide to show, and somehow at the end, the student, so G is not an abelian group. You change the question. You should not change the question. The question already gives you the answers. Sure, it is an abelian group. Tukar-tukar pula. And then you did the mistake and then you said, no, it's not an abelian group. Macam kelakar juga lah. You change the question unless there is a typo kan. Okay, so the first one is G is closed under star. All right. For all A, B, E, G, A star B is A times B over is in G. Right? Because this is a real number which is not zero. This is a real number which is not zero. So this is also a real number and it's not zero. Right? Even if you write like this, it's okay. You don't have to explain anything. Because G is associative. Since A star B star C is equal to AB over 2 star C. A star B is AB over 2. AB over 2. AB over 2. AB over 2, right? AB over 2. So this is ABC over 4. Okay, let me try the other one like this. AB over 2. So C over 2. This is ABC over 2 over 2, which is the same, right? So this is okay. Associative. Then you want to go for identity. Saya buat cepat sikit sebab dah nak habis masa. Okay, you want to say A star E is A is E star A. So A star is AE over 2 is A. EA over 2 is A. Potong kan? So left and right shows you E is 2. Boleh check boleh check. A times 2 is A times 2 over 2, which is A. And this is in G. Don't forget, check. Okay, it's a real number, it's in G. Third one, fourth one, A, apa tadi? A times A inverse is E, which is 2, right? What does it mean? This is A times A inverse over 2, which is 2. A star B is AB over 2, yeah? So A star A inverse is A times A inverse over 2. E is 2 from here, so it's 2. Imagine if you get the wrong E, you get the wrong inverse. So A inverse is 4, right? So A inverse is 4 over A. Not 1 over A as usual, but it's 4 over A. Okay? The other way around, you also get 4 over A. Check. Check. A times A inverse is A times 4 over, sorry, saya punya dot dengan star confused nanti. Okay, star, A star A inverse, kita nak check, is it equal to 2? So A star 4 over A tadi, AB over 2 kan? A times 4 over A over 2. Yay. Okay, it's a little bit fast, but I'm sure you can go back and try and rewrite. So yes, 1 billion is the last time, right? So you have to check whether A star B is B star A. It's easy, right? Because A star B is AB over 2, which is BA over 2, which is B star A. So you start like this. A star B is equal to AB over 2. This is just the regular multiplication, which is equal to BA over 2, which is B star A. So you go around like this, like this, like this, like this. So A star B is B star A. Jangan lupa tulis jawapan. Therefore, G is an abelian group. Some books, they write this capital because a billion comes from Abel. Abel is the name of someone, a mathematician. So sometimes they, from this guy, read through it. It's good to read the history of mathematics. Then they call it a billion. All right, okay? Okay. All right.